Assalamu alaikum wa barakatuh. Bismillah ar-Rahman ar-Rahim. We'll continue inshallah talking about evaluation, and hopefully we'll have time to talk about cross validation also by the end of the lecture inshallah. Last time we talked about multiple evaluation measures, right? What were the evaluation measures that we talked about? Accuracy was the first one, and precision and recall. Okay, and I hope that the differences between them are clear, especially between precision and recall, because that was at the end of the lecture, right? So informally, what is the definition of precision and what is the definition of recall? Informally, we don't have to say it by equations. Just I want you to really understand how these are computed. Precision. How do we compute precision? Yes.
You say how many are predicted as positive, and then how many of them are actually positive.
Are correct predictions. Very good. So how many are positive? Okay. And among them, how many are actually correctly classified, are actually positive? Okay. Right, that's precision. How about recall? Yes. How about recall? That's precision. Yes. Yes. So among the ones that are actually positive, how many we predicted positive? How many we correctly predicted? Okay. So the difference is always in the denominator. The numerator is the same. How many positive are correctly predicted? Always the numerator in both cases are the same. The denominator in precision, we are looking at what the model predicted as positive. In the recall, we are looking at what is actually positive. Okay. Time. Quickly, just to test your understanding, let's do this example together. Okay. So we have these two classifiers. We want to compute precision and recall for each. So how about precision for M1? What is precision? So for M1, where is M1? This is M1, right? So we want to compute precision. Precision of M1. So we should look at the ones that are predicted as positive. The positive here is the red class. So how many are predicted as positive? For M1. How many are predicted as positive? 5. All of the balls in this bin are predicted as positive. Don't be confused. Okay? So all of that bin is predicted as positive, so we should divide by 5 here. How many of them are actually positive? 2. Okay? How about M2? 1 over 3. We have 3 predicted as positive. 1 of them only is actually positive. Right? Do you agree? Any objections? How about recall for M1? How many are actually positive? 3. So we'll divide by 3. How many of them were predicted as positive? 2. Very good. How about M2? 2. M2. 2. How's that? Recall for M2. So how many are positive overall? How many are positive overall in the whole data set? The positive is the red class, right? Is the red balls. So how many are actually positive? This 1, 2, 3, right? Right? So among those 3, how many are actually predicted positive? 1 only. 1 only. Okay, so in this case, the precision and recall is the same. It just happened that way. Okay, but it's not always the same. As you see here that they are different. Okay, can we compute the same for the green class? Assuming that it is the positive class, because it might be the case, right? So we can also compute precision and recall for the other class. Can we do it quickly? How about precision of M1 in this case? Yes, the denominator is 7. And among them, so why is it 7? Because the model predicted 7 as green. Oh, that's M2. Yeah. So that's M2. Good. Someone is awake here. Okay. So that shouldn't be 7. It should be 5. Very good. Because we have 5 here. That's M1. So we have 5 here. Type. How many of them are actually correct? 4. The 7 is here, right? How many are correct among the 7? 5. How about recall? For M1? 4 out of 7. Why is that? Why is it 7 here? Because we have 7 positive, right? 7 green. 4 of them were not 4, right? 1, 2, 3, 4, 5, right? Again, okay, the same. Okay, so that's 4. Yes. How about recall for M2? 5 over 7. Why is it 7? Because we have 1, 2, 3, 4, 5, 6, 7, and 5 of them were correctly predicted. Okay. Any question about precision and recall? Okay, good. Type. Now, in general, as you see, precision and recall are different, right? They are not the same thing. Usually, but it's not always the case. Usually, whenever we try to optimize one, the other will be hurt. Okay, so there is a trade-off always between precision and recall. And the trade-off, you can see it. Of course, this is just one example. It can be like this. As you increase recall, precision will decrease. But there are extremes, of course. So at this point, and let's say at the beginning of and if we are very strict, then we can detect very few positive examples, but we are missing many others. Okay, so the precision will be very high, but recall will be very bad because we missed many of the positive examples. But whatever we predicted as positive were correct. So the precision is perfect, but recall is very bad. So that's this point. There is another extreme, which is the case when we predict everything to be positive. If we predicted everything to be positive, then what should be the recall and what should be the precision? And imagine that a spam filter is saying everything is spam. How about recall in this case? 1. We are getting all the spams, right? But of course, we are getting also so many false positives. Okay, so the precision will be very low, almost 0 in this case. If we have so many emails, then of course the precision will be almost 0. But the recall will be perfect, will be 1. Okay, what's the ideal case? The ideal case is to have both to be 1. Okay, that's very hard to have precision to be 1 and recall to be 1. That means that whenever the model says positive, it is correctly positive, and the model found all positive examples, didn't miss any of them. Okay, that's the perfect classifier. Okay, so got all positives correct and got all negative correct. Perfect classifier. Of course, this is very hard, but that's our target. Type. When we have a classifier, we can, based on the predictions, we can compute precision and recall, as you saw, right? Type. Usually, the classifier produces a number, produces a score. It's like a confidence in the prediction. And usually, the confidence is between 0 and 1. If that's the case, so we tend to take 0.5 as a threshold. So if the score is above 0.5, then the prediction will be positive. And if it's below 0.5, then the prediction will be negative. Okay, so let me show you an example. Let's be again in the spam filtering example that we started last time. And let's say that these are the scores for a specific classifier. Okay, and of course you see the color of the example here saying whether it is actually positive or negative. The red here is positive and green is negative. So if we take the threshold to be 0.5, we can compute precision and recall, right? How? We assume that with that threshold boundary between the positive and negative, everything above that threshold will be predicted as spam, positive. Okay, because that's the spam score. So everything above that will be predicted as positive, and everything below that, if we sorted them, everything below that, then it will be negative. Okay, so at that point we can compute precision and recall, right? We compute it as we did in the previous examples. We count how many are correct and how many incorrect, and we can compute precision and recall. Let's assume that precision is 0.5. If actually you look at this, you will find that how many we have? 1, 2, 3, 4, 5, 6. 6 predicted as positive, and 3 of them are actually positive, so precision is 0.5. And recall, we can also compute it. Okay? Here maybe we are missing the number of all total positive examples. Let's say that there are 10, I think, in this case. So we have got 3 of them, so the recall is 0.3. Anyway, we can compute at that threshold, we can compute the recall and precision, right? Right? Type. Maybe we didn't like the precision here. We want to be more precise. We want the prediction of the model to be more precise. We want the model to have better precision. Okay? So we thought that let's be more strict. Maybe 0.5 is more lenient. Okay? So let's be more strict. Let's make the threshold higher. So we can set the threshold, let's say here, to 0.75 instead of 0.5. The predictions will be different, right? Right? And thus, of course, the precision and recall will be different. So we expect here that the precision to be a bit higher and the recall will be lower. But maybe this is what we want. Right? So at that threshold, we can get different precision and recall. We might also think in another situation, or maybe for the same model, we want to see what happens if we want to get to increase or to improve the recall. To improve the recall, we should lower the threshold, right? Because when we lower the threshold, we get more positive. Okay, so the recall will increase, right? So we lower the threshold to here maybe 0.15. And we can compute precision and recall also for that case, right? So you see here the point is that whenever we set a threshold, precision and recall will be different. So when we model a classifier like that, we can look at these numbers, these different numbers, and see which threshold we should use for our classifier, right? Because every threshold will give us different performance of the model because the predictions will be different. And we can plot these values. So let's forget about the red curve for now. Let's look at the blue curve. This is again recall versus precision. But I think now we understand how we got this plot. Every point on that curve is representing a specific threshold of the score. Remember from the previous slide, whenever we set a threshold, we get a precision and recall value. So changing the threshold, we get a new precision and recall, you get a point on that curve. Change the threshold again, you get a new precision and recall, put another point, a third point, and so on until you can plot the entire curve. So every point, let's say that this point is plotted given a specific threshold. We don't see the threshold here on the curve, right? We can write it, but usually we don't. But we understand that every point here, there is a threshold for it. With that threshold, the precision, the recall is what here? Yeah, probably 0.5, and the precision is maybe 0.85. Okay? If we another point is this point. In this point, the recall increased to maybe 0.8, and the precision is 0.7. Okay, and so on. So every point on the curve is about one threshold. Okay, so every point actually is a different classifier. You can think of it that way, or a different configuration of the same classifier. Okay, when we configure the threshold, when we tune the threshold, we get different precision and recall. So looking at this curve for one model, it can give us an idea of how the model behaves if we change the threshold. Precision and recall will give us just one point on that curve, but we don't know if we raised or lowered the threshold, what will happen. So in this case, for example, if this is threshold T1 and this is threshold T2, do you think T1 is less than T2 is less than T1 or greater than T1? And looking at the previous slides, when we increase or lower the threshold, what will happen to the recall? Here the recall increased, right? And if you look at here, in that point, the recall increased. The recall became 0.8 instead of 0.5. Okay? Recall increases usually when we lower the threshold, because now we are more lenient, right? We are not strict, we are lenient, so we get to predict more positive examples, so the recall will increase. Okay? Did you get that? You had a question? Yes, it is binary classifier. Because we have to at some point. Okay, now binary means that you will have to make binary decisions, right? And whenever you get an example, you have to say positive or negative. Usually the classifiers, most of the classifiers, produces a score before making that decision. Yani confident, yes, exactly. It's actually called confidence score. Okay? Yani, let me give you an example. KNN. You remember KNN, right? Yeah. In KNN, let's say that K is 5. Okay? And we want to make a decision. How do we make the decision? We get the 5 nearest neighbors, and then we see the votes, right? If all the votes are positive, we will predict positive, right? If 3 of the votes are positive and 2 are negative, still positive. But how about the confidence in each? With the 5 positive, we are more confident than 3, right? So a score here can be the number of positive divided by the number of negative. So for the 5 positive, the confidence is 1. For 3 versus 2, it's 3 over 5. Okay? So many of the classifiers work that way, actually, before giving the binary decision. So there is a threshold. We have to make a decision. Above this, it will be positive. Below this, it will be negative. Okay? Did I answer your question? Okay. Other questions? Right. Now looking at these two curves. If these two curves belong to 2 different models, and now we understand that every curve is for one model, but with changing the threshold, the score threshold, right? Which one is better? The red one. Why?
Because we have, when we have a higher recall, we also have higher.
Yes, because it's above the other one, right? Above means it's always higher recall, higher precision. Okay? So we can look at the curves and we can say, yes, one curve is always above the other, then of course it is better. Even without setting a specific threshold, we are now thinking about the model in general, in many different configurations. Okay? Even if the threshold changes, it will be still better, right? But that's not easy. Yani looking at maybe plotting the curves and looking at them, it's not easy. Okay, but it is done. If you want to really to study how the classifier behaves, is it really stable? If I change the threshold a bit, will I have a completely different performance, or still good enough? So with that curve, which relates recall and precision, you can have an idea about how your model or how your classifier behaves. Okay, any question about this? Right. Now, when in reality, will you have different thresholds? No, in reality, you will use one of them. But you can look at that curve and say, okay, I lean more towards recall because in my application, recall is more important. So you get specific point on that curve, you see what threshold, and then you use that threshold. Okay, so in reality, you will use one, of course, 1 point on that score, on that curve. Right, because in reality, you want a classifier that will make decisions based on a specific threshold that you can pick from that curve. Type. We studied now precision and recall, and these are two numbers, right? It's always preferable to just compare one number among different models. It's a bit harder to compare two numbers, right? What if we are comparing two models and precision here is higher and recall here is higher? Which one is better? It will be hard for us to decide, right? It's easier if we have just one number from here for that model, one number for that model, and we compare them, right? Type. Now we have both precision and recall. Let's say that we have one number for precision and one number for recall. How can we combine them into one single number? What is the easiest idea of combining them? Average, right? We can average them, right? Precision plus recall over 2. Type. If you notice, what is the range for precision and recall? Is there any bound for precision and recall? Is it always between 0 and 1, right? So it's always between 0 and 1. Yani whenever you calculated it and you found it's 1.2, you know that you are completely off. Okay? Or minus 3.7 or minus 0.01, you know that it's completely off also. So it's always between 0 and 1. So the average of them will be also between 0 and 1, right? Very good. Now, let's assume that we have a classifier that has perfect recall, almost 1, but very bad precision, almost 0. What will be the average of them? 0.5, right? So the average will be 0.5. Is that classifier good, actually? It's a very bad classifier, right? Recall is 100, yes, but precision is very bad. That's like a classifier that is always saying positive. I can get 0.5 in this case easily. Say always positive, you will get 0.5, right? That's not good. That's not a good measure. 0.5 is a large number between 0 and 1, right? In this case, we want a number to be closer to 0, right? And we want the performance, in this case, the performance measure that we should use should be closer to 0 in this case, right? When we have almost 0 precision and 1 recall, or even the opposite, you want the performance measure that you will use actually to be closer to 0 than to 1, not in between, not exactly in between. Did you get my point? Okay, so my point here is that the average, or what we call the arithmetic mean, which is the average, is not the right way to combine them, because it will give us higher numbers even if the classifier is really bad. So what we do is to use what we call harmonic mean. Harmonic mean, not the arithmetic mean. The harmonic mean, the property of the harmonic mean is that if we are computing the harmonic mean of two numbers, it will, like the arithmetic mean, it will give me a number between them, but it will be closer to the smaller of them than the higher of them. And that's what we want in our case, because we want, whenever a classifier has bad precision or recall, the measure of it eventually should not be good, should be closer to the bad value. Okay, so we reward more the classifiers that are good in both, not just one of them. Did you get my point here? So the harmonic mean in mathematics, it is the inverse. So you know the arithmetic mean, right? It's 1 over the number of the values times the sum of these values, right? The arithmetic mean, the harmonic mean is 1 over the average of the inverse of them. Okay, so we have precision and recall here, right? So the average of the inverse of them, so you get the inverse of each one. So 1 over P plus 1 over R over 2. So that's the average of the inverse, right? And it is the inverse of that. So that's the harmonic mean. If you do this, you will get this formula. Okay, so this is called F1 for a reason that you will know very in few minutes, and it is computed as 2 times the multiplication of both over the sum of both. 2 times precision times recall over precision plus recall. Now let's get to the example that we just discussed, when one of them is almost 0 and one of them is 1. Let's say 0 and 1. What will be the value in this case? 0. 0. Okay? As I said, it will be much closer to the one that is the smallest of them. The arithmetic mean will give us 0.5. We don't want this. We want a measure that will punish the classifier that has one of them to be really bad. Yes?
I think I missed something. You just said that we cannot compare two different things, but now we're doing like the precision and the recall. Didn't you just
No. Okay. What I said is that we cannot easily compare two numbers against two numbers. Yani, we have two classifiers, okay? We want to compare the performance of these two classifiers. It would be much easier if I can evaluate the performance of each using just a single number. And I can say the performance of this is 0.7 and the performance of this is 0.5. Then I know that 0.7 of course is greater than 0.5, right? But with precision and recall, I have two numbers here and two numbers here. So I have to combine them so that it will be easy to compare two models. Okay, you got to the point now? Any other questions? So this is how we combine them actually, precision and recall. 2 times precision times recall over precision plus recall. Type. This measure deals with precision and recall equally. Yani it doesn't give more credit or more consideration to one of them. What if in my application precision is more important? So I want a measure that will reward more the classifiers that have higher precision. Or the recall is more important, so I want that also. So a general formula for the F measure, so this is called the F measure, okay? A general formula of the F measure called weighted F measure. In the weighted F measure, it has a parameter called beta. So if you look at this formula and compare it with this one, what's the difference? You see that here we introduced beta square plus 1 instead of 2, and beta square here instead of 1. Actually, if you set beta to be 1, what will happen? So let's set beta to be 1. What will happen? We will get F1 measure. Exactly. Okay, that's why F1 is called F1, because that's the F measure when beta is 1. Okay, so this is the general formula. F1 is a special case of this when beta is 1. When beta is 1, that means that I want to treat precision and recall equally. Okay. Do you have any questions? Yes. I'm worried because you are not asking so much today. You also, I'm worried about you. Are you okay? Okay. You understand everything, or you don't care about this lecture? Okay, good. Yes.
Is it beta equal to?
We'll get to that. Okay? But at least beta is 1 means F1. خلاص? طيب. Let's say beta is 0. What will happen? يعني beta is 1, we will get F1, right? طيب. Which means in precision and recall are equally treated. Type. If beta is 0, what will happen? Okay, when beta is 0, what will happen? Say it again. PR over? Beta is 0, so this will be cancelled. R. So it will be very good. It will be only precision. Okay, so we get here just precision. So in general, beta is between 0 and infinity actually. Okay, we don't put beta with minus. When beta is between 0 and 1, we are favoring precision. Okay, to the extent that when beta is 0, that's the limit, it will be purely precision. Okay, in between, it will be more precision than recall. Type, if beta is greater than 1, we are favoring recall. To the extent that when beta is infinity, and you can do that yourself, you'll find that the F measure will be just R, just recall, when beta is infinity. Okay, so usually we say it that way. If beta is let's say 1/5, then precision is 5 more important than recall. If beta is 5, then recall is 5 times more important than precision. Okay, so we say it that way. Type, which one we should use? From 0 to infinity. Depends on what? On the, not the model, the application. If the application is recall oriented, the recall is more important for that application, then we set beta to to greater than 1. Okay, if the precision is more important, then beta is less than 1. What if we don't know? Just set it to 1, and this is the standard. In most cases, we just use F1, unless we really understand that the application, in that application, we want to favor recall or precision over the other. Okay, is that clear now? So did we get 1 point, one single number, this way? Yes, we compute precision, we compute recall, and then we compute the F measure, whatever. Usually we use F1. Any questions? Right. Let's see an example quickly. So this is the same example that I think we had in the previous lecture. So precision is and recall is already computed. How about F1 for M1? How do we compute it? 2. So do you remember the formula? 2PR over P plus R. That's F1. So 2 times 0.33 times 0.5 over time. What do we expect before we actually compute it? What do you expect the value to be like? Yani, that's even without looking at the numbers at all. It's always between 0 and 1. Yes. Okay. But knowing that the precision is 0.33 and the recall is 0.5, which is what? Which is 0.33, right? So it will be, of course, it will be between. It cannot be outside 0.33 and 0.5. By the way, that's another check. Okay. And if you got 0.7 in this case, you know that there is something wrong. Okay. It will always be between them, but it is closer to 0.33 than 0.5. How about this one? Calculate it, please. 0 over 0, not 0. 0 over 0 is not 0. But we actually consider it 0. So you are right, but you are wrong at the same time. Okay? So this is a very special case when both precision and recall is 0. Of course, it will be 0 over 0, which is, to my knowledge, is undefined. But in this case, we know that the classifier is very bad, right? 0 recall, 0 precision, that's useless. So the F1 here will be just a special case, 0. Okay. Right. So we have 0.4 and 0 here. Any question about this? So any question about precision, recall, F1 should be easy to do, right? You understand it's not just applying the formula, you understand each one of them, I hope. Questions? Questions? Questions from this side? Type. Everything so far was based on the fact that the classification was binary classification. So we had how many classes? 2. But in reality, you might have more than 2 classes, right? This is what we call multi-class classification. Okay, in multi-class classification, we have more than 2 classes. Actually, in this specific example, we have 3 classes. We have green, red, and blue. What should we do when we do the evaluation? Can we still use precision and recall and F1? What do you think? Yes, we can. It's very straightforward, as you will see. Very straightforward. Okay, how will we do it? Right, before that, let's compute the accuracy. What's the accuracy here? 3 plus 3 plus 1. Very good. Yes. Which is 7/10. Okay, so that's accuracy. خلاص؟ طيب, what's the problem? The same problem that we talked about last time, that it treats all classes equally, and if there is any imbalance, that will not be fair. So good measure, the accuracy is good measure when classes are actually balanced. طيب, let's assume that the classes here are not balanced and compute first the confusion matrix. You remember confusion matrix from last time? Can we compute it also for this? So before it was 2 by 2, right? Because we had 2 classes. So we can predict 2 classes and the actual are 2 classes. Now we have 3 classes, it will be 3 by 3. If we have 4 classes, 4 by 4. Okay? Type. Can we compute the first row? What's the meaning here? For this cell, for example. This is predicted green and actually green. How many? So confusion matrices are just counts. Okay? So how many are predicted green and they are actually green? 3, because this is everything that is predicted 3, not predicted 3, predicted green, and 3 of them are green. So we have 3 here. Type, how about this one? 0. Last choice? 0. Any objection? Right. Okay, 0. Then 1. So this is predicted blue and it is green, right? So it is 1. Very good. Right. Can you give me the second row? 0. 0 predicted as green. Okay. And how about this one? 3. How about this one? 0, 1. How do you get this number? Predicted blue, actually red, right? Where are the predicted blue? Yes, C3. How many of them are red? How many of them are red? C3, you said C3, right? How many here is red? How are red? 1. This one? 1, 0, 1. Okay. Any objections? Type. Can we compute precision and recall for each of these classes? Precision? Yes. Yes. Very good. So that's 3/4. Precision for 3/3. Okay. 3/3. How about blue? Very good. Type. Recall here. 3/4. How many green we have? 4. 1, 2, 3, 4. How many we got green? We predicted as green? 3. Okay, so that's 3/4. 3/4. Okay, we have 3 and all of them are 4, right? The red one are 4, right? What's the recall of the blue class? 1 over? Why is it 2? I'm not saying it's correct, it's wrong, by the way. I'm just asking you. Why is it 2? Because the number of blue is 2 only, and the one we got 1 correctly. So it's 1 over 2. طيب, how about F1? Why is it 0.5? 0.75 times 0.75, right? Over 0.75 plus 0.75. What do you expect in this case? Yeah, logically, both are 0.75, and we said that the number will be between both. What will be the number? 0.75. So when precision equals recall, F1 will be that value. Okay, so we expect that will be 0.75. Type. How about this one? Quickly. Okay. 2 times 2 times what? This is 3. 1 times. No, why is it 3 over 4, sorry, yes. Okay, divided by. Okay, and this one 2 times 1 over 3. Okay, over. Very good. Type. Now we computed F1 for each class, but we didn't say what is the performance measure for the entire classifier, right? Right? That's per class. But we also need one number. So in this case, we use what we call macro F1, which is the average of them. So we compute F1 for each class and then average them to get just one number, which is the performance measure for the classifier as a whole. Okay, that's if we care about all classes. But if we target only one class, then we have the F1 for that class. Then we compute the F1 for that class. Any questions? Yes. Raise your voice, please. The average between what? The average precision? يعني you compute average precision, average recall, and then you compute F1? I didn't get your point. You are asking. Okay, I got your point. Okay. So you're saying we can compute average precision, and we can compute average recall, and we can compute average F1, right? Which is macro F1. Which one we should use, right? What do you think? Okay, so the question again. From that table, we can compute average precision, average of these 3 values. And we can also compute the average of these 3 values, which is the average recall, right? And we can also compute the average of F1, which is macro F1. Which one we should use as a performance measure for the classifier? Why is it macro F1? Because that's the reason we had F1, right? Is to combine both precision and recall. We don't want just to report one of them. We want to report a measure that considers both, and in this case, for every class, not just for one class. Okay? Right, we'll stop here. Inshallah, we'll continue with cross validation next time.